just as kind of like a review or a reminder that, okay, we have gamma, which is statements paired with states. And remember, states are just the functions, the partial functions from variables to ints. And so state is a kind of a big thing, right? These functions are, you know, mathematically speaking, this is a function is a kind of a large object. Statements are all the possible statements. There's countably infinite number of statements. There's, you know, countably infinite or even more number of states. And then you union that together with states. And so then the terminal configurations are states. So you just go to a state in the terminal configuration, as you can sort of see on the rules below, like that's a single state, that's a state, that's a state, and so forth. So we need to have states alone in the configuration, and then states paired with statements. And the arrow function, the big step semantics, takes, remember, formally, it has to be a subset of gamma cross gamma. And in this case, it's a subset of statements paired with states. That's one part of gamma, paired with states. So in the big step semantics, you never have a rule that evaluates to something that's not a state. You never sort of partially evaluate a statement. All the rules are going to completely, when you look at the big step semantics, you're evaluating essentially the entire program all at once to its value. And its value is the memory, that state of memory that you have after you evaluate the program. So last time we pointed out that, okay, this is really, we may look up, well, really, this is the only, it's a little bit crazy in a way. I mean, so to look up the meaning of a variable in an arithmetic expression, we use the state. We apply the state to the name of the variable, and we look up the value stored by that variable. And then again, here in statement, this is the only statement that actually does anything with states. All the other ones just use them occasionally to try to evaluate something, like here, or even in this assignment statement, it looks at the evaluation of A in a state. So there could be variables in arithmetic expressions, remember. But this is the only one that actually really does anything with a state. And what it does, it says, look, if you want to evaluate the command which assigns the value, let's see, X gets the value of the arithmetic expression A in state S, what do? The result is a state. And what do? You take S and you just update the location of the variable X to now have the value V, where V is the result of evaluating A in the current state. So you kind of like, you know, look at this package, you say use S to evaluate A, you get back a V, and then what you do is you return, you know, if you're thinking of this as like evaluation of this evaluates this, result is the new state S, where X gets the value of V. Skip is dead simple. It just takes a state S and returns S. So skip is a no-op. It just doesn't do anything. Now, oh, that's interesting, right? That is an annoying thing that it's not, it doesn't obviously stick to the thing I'm writing on. So what about this sequencing statement here? So when I say, okay, look, you want to evaluate S1 and then evaluate. So you're here, you evaluate S1 and then evaluate S2. So what you do is you take S1 up here and you take S and bring it up there. And you take S1 and S and you get S double prime. And then you take S2 and then you take this S double prime over here, and now you evaluate S2 in the state that you got from evaluating S1 in S, and that gives you back some S prime, and that's the result of evaluating S1 followed by, this is a sequencing operator, followed by S2, where S1 and S2 are statements. So, maybe I should do like a little thing over on the side. Like we have enough, we have enough to do a little evaluation here. Like suppose I said, oh, where am I? Over here. All right. Suppose I said, evaluate X gets the value of 1 followed by Y gets the value of 2 in, and now I need a state. And the default state could be the empty set. I don't know, maybe that's a little weird to imagine, but it's the state that doesn't know about any variable. So we could say the empty set. And now we want to say, what does that evaluate to? Well, the rule for semicolon says go up here and evaluate X gets the value of 1. Well, sorry, I am worse today than ever on this thing. I don't know what's going on. Whoa, that's terrible. Okay, so I'm just trying to grab the eraser and erase this and make this a little better. Okay, so over here we have X gets the value of 1, and the state is the empty state. And so what does that evaluate to? Well, that evaluates to a single thing that says, oh, X it's the state where X gets the value 1, and nothing else is in that state. But then I have to figure out now what to do about Y gets the value 2, and so I'll do it up here. I'll say like Y, it goes over here. Y, the statement Y gets the value of 2, and now I'm evaluating this in the state where X goes to 1. And the rule says evaluate the expression A. My expression A is 2, so that maybe I should draw a little this is a numeral. And so then we get 2, the value of 2 under any assignment is just 2, or under any state is just 2. And so now what do? I take and I return the state that has x going to 1 and y going to 2. And so this line is over here. This thing is over here. And so down here, what we return in the final analysis, is that we return this state. X goes to, oh my God. This is horrible. This doesn't work. We go to the state over here that says X is 1 and Y is 2. So that's the final state.
What?
Okay?
It's bad. It's
So
pretty waste of time.
Somebody needs to turn off their microphone. Thank you. So anyway, clear all. So we have enough just from these first 3 rules to do some, semi-interesting computation. Okay, evaluate the program that assigns x1 and y2 starting with the empty state. This rule applies, and then this rule applies on the left side, and then this rule applies on the right side. The if rule says, if this piece of syntax, if B then S1 else 2 in state S evaluates to S prime, well, but to show it, the first thing you have to do is you have to take B, the Boolean condition, evaluate it in the state S, which is the one that's packaged up here. And if that returns true, then you pluck this S1 out, you pluck S out, bring it up, make a new package S1S, and then you evaluate whatever that evaluates to, and that would be an S prime, and so you return S prime. And then the false rule is the same, except now you choose S2 to evaluate, and you get an S prime. Now, you could combine these rules into one by saying something like, okay, if B then S1 S2 in state S evaluates to S prime, where S sub I and I is determined by B. If I is true, then I is 1, you evaluate S1. And if if B is false, then I becomes 2. And so then you evaluate S2. So this rule would work for that. But we'll see below that it turns out to be kind of important to not try to evaluate both S1 and S2, because then you kind of lose expressiveness of certain kinds of programs. And I'll show you an example. Now, the while rules, I mean, I think you've done enough programming. The while rules should make perfect sense, but they're not compositional. I'm trying to define the semantics of while, and so while occurs on the bottom line, but to do it, I'm using the expression while itself above the line, and so that means I have a premise. When I'm trying to evaluate while B do S, part of the rule for evaluating says, evaluate while B do S in some different state. So the first thing you do is you look at B and you say, okay, if B is true, then this rule applies. If B is false, then this rule applies. So maybe it's good to look at this one first. What if the condition is false? Then the while B do S in state S just returns state S. It's a no-op, just like skip. So if this B evaluates to false in the state S, then you just return the state S. You don't do any work. But if B evaluates to be true, then your while statement, to evaluate this while statement in state S, the first thing you do is you take the body of the while statement, which is S, evaluate that in this state little s, and you get back an S double prime. And now what you do is recursively evaluate the while in state S double prime. And if that produces a state S prime, then that's the result of the original while that you started out to evaluate. So, you know, presumably, I mean, one exercise that we've done in the past in this class is to like say, okay, well, look, this could be the basis for some analytics, some static analysis of a program. So normally when we're talking about programs, we talk about dynamic properties or dynamic analysis or properties that can only be discovered by actually running the program. Static properties are properties you can get just by looking at the syntax of the program. And these semantic rules give us enough that we could sort of say, look, well, it's going to come up in just a second, but yeah, we're going to prove a certain program does not terminate. But maybe let me see if I'm any better on the, I don't know, on the sharing the whiteboard instead of writing on this thing for some reason. I have no idea why I would be. So the point is that if we had a while statement, I'll make that black. If we had a while statement, you know, B, now suppose B has no variables in it whatsoever. So B is some kind of Boolean expression that only has an arithmetic, you know, equality on some arithmetic expression, or greater than or less than. So, you know, suppose
So
that,
like a constant.
so it turns out it's a constant in any individual state. Yes, it will evaluate to a constant. So I guess I want to say, like, you know, suppose B has no variables, then it is a constant, because no matter what state you evaluate it to, it evaluates to the same thing. So suppose B has no variables. Then B is a constant. And that means that, you know, i.e. B is equal to true, or, not of, or B is equal to false. So if I say, so then I have like, okay, while true, do S, that is going to loop forever, because evaluating S never changes. So this just goes on forever. Evaluating S can do nothing to change that B is equal to true. And then while false, do S just evaluates to S in state S. I mean, so I guess I need a little bit more information here, right, to make this technically correct. But it sort of doesn't depend on, the point is it doesn't depend on the state, but I can put the state in there, maybe. And that's a little s. And so that just keeps going. And this one just evaluates to s, so it's the same thing as a skip. So I would claim that if you wrote a program like this, you've made a mistake, because you could have either written skip and so that just evaluates dash. You could have just written skip, or this one never terminates. So this has got to be kind of an error. So then, but you can look at it a little bit more deeper. You say like, okay, so let's see, let's consider. You could write like a kind of a checker for a program. And you could say, okay, what are the variables in B? Okay, suppose that, like, I don't know, X, Y, and Z are variables that occur in B. And then you look at the variables that are in S. And maybe what I want to say is not just the variables in S, but the variables in S that are on the left-hand side of an assignment statement. So, you've got something like, I don't know, W gets the value of A. There might be variables in A, but I don't care about them. I only care about the variables that are on the left-hand side, because those are the only variables that can change the evaluation of B over time. And so there's like a little theorem we could prove that says, that if the variables in B intersected with the, I don't know, we could call them like L values, because that's what they're called in like C and C++ and most programming languages. The variables that occur on the left-hand side of an equals are called L values. If that's empty, then the program is in error. Because now it could be that the program's still in error. It could be that, that like, let's say you've got something, or first of all, are there any questions on this? The point is that, go away, is that S stops the while loop by changing something in B that makes it go from true to false. And so the only way that can happen is if you have some value in S that's on the left-hand side of an assignment that's also one of the variables in B. But you could still have a bad case of like, you can see me writing here, yeah? You can see that.
Yeah.
Somebody help me. Can you see this? I'm
Yes, we
scribbling.
can see it.
Yes, we can.
Okay, thank you. I all of a sudden got nervous that I wasn't sharing this particular screen. Okay, so, I could write like a little program, while X is, I don't know, whatever, greater than 0, do X gets the value of X. Now, this would be a bad program too, but this wouldn't pass the naive test because, this is just going to loop forever also, because even though I'm changing X here, I'm updating X. X is an L value here. I'm not actually changing X. So if X is greater than 0, this program will loop forever. And if X is less than or equal to 0, this program is equivalent to skip. So this one's an error, but will not be caught by the previous criteria. But the intersection idea is very, very simple. It's a very simple thing to check. And, it could be helpful to beginning programmers to be able to check this. I mean, once you get past a certain level, if you do this as you could still make a typo and have, you meant to write an X on the left. Pardon me. And instead you wrote a Y or something, or an X prime. So we can use the semantics to kind of evaluate, consider different okay, let's go back here. So you can use the semantics to do kind of program analysis on the program. Now, this to me is kind of sad. I mean, on page 52, near the bottom in the new section called Termination Big Step Semantics, he makes some definitions that he doesn't even give numbers to. And I have to say, it's pretty easy to read the book. And if you kind of like, are reading quickly and don't pay close attention to this, it can have some real impacts on your understanding later on. So the thing that is defined here is, what does it mean for the execution of a statement S to terminate from a start state little s? And we say it terminates if, when you look at the rules up here, you can use the rules to find an S prime such that S comma S arrow S prime, so that these S and big S, the statement S and the state S, that pair is in the relationship to the state S prime. So, I mean, you can write it a little bit more mathematically. S terminates from state S if and only if there is some state S prime such that the statement S and statement S evaluates. Oh, there should be a prime on that S. Does that make sense? Well, we'll see in a minute some things that don't terminate. So we say a statement S loops forever on state S if there is no state S prime such that S, the statement S in state at little s, evaluates to S prime. So it loops forever if there isn't this state S prime. So we can also write S loops forever, statement S loops forever on, I wish he had used sigma for states, but all right, on state sigma if for every sigma prime, S paired with sigma does not evaluate to sigma prime. So if there's no place you can go, now what would that mean? Like, currently, and I didn't write down on the top of this the syntax for statements, but currently for statements, there is no, like we have a rules for every piece of syntax in statements where the rule occurs, on the left-hand side of the pair on the left side of the rule. And so it's kind of interesting. What would it possibly mean for something to loop forever? How can there be no state? So in a more formally, we just say S loops on sigma if for every sigma prime, S comma sigma does not evaluate to sigma prime. Now, S always terminates if for every state S, S terminates from starting on S. And S always loops forever if for every state S, S loops forever on S. Okay, so here's a really concrete example, and it's problem 4.8 on page 52. And it's an important theorem because you get to see quite a few things here. He says, suppose S is the program while 0 equals 0, do skip. So first of all, somebody want to volunteer what this program is going to do?
It's not going to do anything.
Well, it's going to loop forever by our rules. Because 0 equals 0 will evaluate. So you're right. It's not going to do anything because it'll loop forever. It's going to say like, oh, okay, this will always evaluate to true. So this rule always applies. So then it looks at S and it says, okay, this big S, our command is skip S, S is S. And so then we end up over here trying to evaluate exactly the same thing over again. And the tree never results in we get like, if you just keep building the tree, like if you were a computer blindly following the rules, you might just keep trying to build the tree, even though human might notice, oh wait, we're trying to do the same thing over and over and over again. So this program loops, it always loops forever, always loops forever. It doesn't just loop forever on some particular state. So we can show this by, so this goes back to this like kind of most fundamental idea here is that we're defining the we're defining this arrow relation, which is a subset of statement cross state cross state. So arrow is a relation, and we're defining it using these rules above. And so remember that, you know, for some state S and some, I'm sorry, for some statement big S and some state little s, that's in the arrow relation to some little state, some state S prime, if and only if you can use these rules to build a finite derivation tree. So this only occurs when there is a derivation that shows that this goes to this. But if we try to build the tree for this, we end up trying to build an infinite tree. So we can show by induction on n, where n is the height of the derivation, that there's no derivation tree of height n showing that there's an S prime that this program evaluates to. So maybe I should be more explicit here. I mean, we're trying to show that we're trying to show that, come on, for every state S, this program, and I mean, I call it loop. I could call it loop. I call it loop below. For all this, there does not exist. Oh, I'm going backwards fast as I'm going forward. Okay. For every S, it's not the case that there exists an S prime such that loop, comma, S evaluates to S prime. So that's what we're trying to show. And we're trying to prove it by, you know, this thing here, this is in the relation with this, in this arrow relation, if we can build a derivation. And every derivation has a height. And a derivation has a height 0 if it's one of the rules that has no premises, like this one or skip are the two rules that have height, where a proof of a particular, of this form, the derivation of this form has height 0. A derivation of this form has height 0. A derivation of this form has height, which is the maximum of the height of this one and this one. So, you know, those two have some height, plus 1 because we go down 1. This one has the height of this derivation plus 1. This one has the height of that derivation above plus 1. While has the maximum of this and this plus 1, and the height of this one. Oh, that's an axiom also. So we have 3 axiom cases, and we have, but the other rules all have some height for them. Okay? Does that make sense? So the height of the derivation, you can, it's like the height of the graph. So we want to show on induction on n that there's no derivation of tree of height n. Now the base case is, so we've got some specific program. So the only derivation of height 0 for a while statement, I mean, loop unfolds to be a while statement, right? What we're really dealing with is this while statement, right? And so the only rules that apply when we have a while statement is the piece of syntax that we're working with is one of these two rules, while true or while false. But the only one that has height 0 is this one. But if this one has height 0, then S must evaluate B to false. But we know that S evaluates B, which in our case is 0 equals 0, always evaluates to true. So that rule can't be a derivation showing that this thing is in the state in, that there's a derivation of height 0. Okay? Questions? There's only one rule that applies to a while if we assume the derivation has height 0, and that's the rule where the condition is false, but 0 equals 0 is always true, so this rule does not apply, so there is no derivation of height 0. So now, I don't know, this proof is maybe a little bit tricky because we haven't really gone over inductive proofs to remind you, but I mean, it's one of those things that we went over extensively in functional programming and that you learned, probably way too much of in discrete math, and I don't know, does Lars use induction in 3020?
Yeah.
So you've seen a
Yes,
lot
it
of
does.
it, but it's always a little, unless you use it regularly, I think it's a little hard to kind of like internalize. So what we get to assume is that there's no derivation that for the statement, which is this while, that terminates in some state S. So then we show that there can be no derivation tree of height n plus 1. So there's no derivation, I'm sorry, I didn't say it correctly. There's no derivation tree of height n, that's what we get to assume, that shows that S terminates. And so then we show that there can be no derivation tree of height n plus 1, showing that the statement S terminates in some state. Look, you suppose there was. So we know that now we're dealing with, n could be 0, but we kind of already showed that you couldn't have a proof like this where this was 0. But so we're somewhere where it's a huge tree. Let's say after you did this, for 5 years, you kept blowing up that derivation tree. For some reason, it suddenly showed it. I mean, It seems so obvious, so it's like a little bit hard to imagine why do we have to resort to induction. But we do, because that's the only way that we can prove something about something being in the relation to some state is by looking at the derivation trees. So suppose that there was, I mean, what would it have to look like, this n+1 derivation? Well, we know that this evaluates to true, so at least this time we're kind of like applying the right rule. We're applying this rule. And so the derivation is going to look something like this. It's going to look like while 0 equals 0, do skip in S goes to, and then that some S prime, we're assuming. And then you'd have skip up here. And, you know, because we're in the case where this is true, so we evaluate skip, and so we evaluate S. And so we end up back in exactly the same state. And then this derivation here, though, is one of height n, not n+1. And we know there's no derivation of height n, so there can't be a derivation of height n+1, because this one would be a derivation of height n. And we already assumed that there was no derivation of height n. So there can be no derivation of height n+1. All right, so how bad is that for everybody? Maybe it's not bad.
It makes sense.
Okay, good. Yeah, I mean, if you're okay at this, it makes sense. But sometimes a lot of students struggle with inductive proofs. So now let's go back and just look at the one comment on the if is that so suppose loop is this program, while 0 equals 0, do skip. And we've shown that for every S and S prime, loop S cannot go to S prime. So the loop program always loops forever. Now consider this program. If 0 equals 0, then skip, else loop. So we say, okay, use the if rule, and 0 equals 0 evaluates to true. So we evaluate this thing, skip, in the same state S. That's what the if rule says. And skip S evaluates to S, so this goes to S. But suppose we wrote the rule like this. We said, so this is kind of like a meta comment on the nature of writing down these rules. Suppose we said, look, here's the if rule. If B, then S1, else 2 in state S, to evaluate that, evaluate S1 in state S and get back S1, and evaluate S2 in state S and get back S2, and then look at the Boolean condition and figure out if it was true, then you take back S sub I where I is equal to 1, and otherwise you take back S sub I where I is equal to 2. And this might look like a perfectly good rule, except that if we tried to use it with this program here, with this program here, we say, okay, if 0 equals 0, then skip, else loop S. And so now we say, okay, yeah, on this branch, evaluate skip in the state S, and that returns S. And on this side, evaluate the program loop in the state S. And the rule says it has to go somewhere. But we know that loop S never finishes evaluating. So if we had a rule like this, we would be saying to figure out the meaning of an if then else, you always have to evaluate the then clause and the else clause, and then we select it. And, you know, then this program would not be a legal, this program would be one that never terminates, even though 0 equals 0 is true. So skip is really the only one we need to evaluate here. And so this is a kind of what we call lazy evaluation that is built into if in almost every programming language you know, except Haskell. You need lazy evaluation to have an if. Well, no. All right, I said that wrong. This is a rule for if in every programming language you know, including Haskell, where you evaluate the Boolean, and then based on the Boolean, you either evaluate S1 or you evaluate S2. Now, what I was thinking of is that in all the programming languages that you know, you might think of like, okay, write a function called, I'm going to write a function called if, oh, I don't want it to be yellow. I don't like yellow functions. Let's see. Let's make it a black function. So if I wrote a function, let's say f, and it takes 3 arguments, the b, and I'm going to write it so it looks like I'm writing in your favorite language, and then, you know, S1, S2, S is equal to now, okay, so I don't know. Here's the problem with sometimes trying to do these things off the what I'm showing or trying to show right now is that in every programming language that you know beside Haskell, if you try to implement a an if with a function, and you say, oh, that's just equal to if b, then S1 else S2. Now, what's going to happen with this if you try to implement something like this is that every function in all the programming languages you know have eager evaluation. So they're going to evaluate B, they're going to evaluate S1, and they're going to evaluate S2 before they go down in here. And if S1 or S2 loops forever, then this thing is going to loop forever. Whereas in a lazy language or in a real if then else like this, like the ones above, with, you know, real if then else rules, you don't have to worry that the other branch is going to loop forever, because you don't even evaluate it. You look at B first, and it's the same thing here. I mean, to figure out this rule, you know, you gotta know whether I is equal to 1 or I is equal to 2. Questions? Okay. Now we can look at the small step semantics. I don't know. I guess maybe I should say something, one more thing, maybe. I don't know. I don't know. Are there any other questions on the big step semantics? One thing that I might say is that, you know, on the big step semantics, we're evaluating some program in some state going to some state as prime. And this derivation could be very big because you're evaluating all the way to S prime. And there's only one derivation on the way, but in the small step, so this is, big step. In the small step, we can have lots of like little derivations that say, okay, this evaluates to S prime, comma, S prime, and or maybe I should call it S1, some new statement. S1, comma, and some new state, S1. And then we could have another one, and that has a derivation, but the derivations for short step are usually short, or small step are usually small derivations. And then we could have another one, for S1, comma, that says that, oh, and by the way, big S1 and state little S1 also evaluates to S2, comma, S2, and this one will have its own derivation. And eventually we'll get to a state that's a single state S prime. And one of the things we're going to prove below is not today probably, is that the big step and the small step semantics give the same answer if you follow the small step semantics far enough along. Okay, so here's the small step semantics. This rule is identical. So the rule for assignment works the same. It evaluates this pair all the way to an S. Now you could, you could do something. It depends on, in a way, it depends on your purpose for the semantics. Like suppose this would basically say, okay, from one step, I can go from here to here. But that doesn't say something about this. Like that doesn't say what to do. That evaluating an arithmetic expression could be a hugely complicated expression that could take a lot of time. But you're saying, no, whenever, every assignment gets evaluated essentially in time one by going here. We could write, if we wanted to keep track of the small steps evaluations of A, we could have a new rule that said something like X colon equals A in state S evaluates to x colon equals a prime in state S if in state S the small step semantics for A says A small step evaluates to A prime. So now if we did this, and if you go back in the book and look at the small step semantics, it basically said, oh, look, if A was, like an addition of two terms, evaluate in the left side or the right side until you get down to values. So this would count all the steps that you did in your small step semantics for A. If you wanted to build that in, you could. So this is, small step semantics. For A expressions. But in this case, we're not doing that. Like, you might want to do that if you really wanted your semantics to try to, like, in some way characterize the actual complexity of computing a thing. You might want to count arithmetic and even Boolean operations also. You could do the same thing on these that evaluate a Boolean. The rule for skip is the same in this. That looks the same as it did before. Now, this one's different. So if you have a composition of S1 with S2, you take S1 and you start evaluating it, and if it goes to a pair, then the result, so it goes to, it doesn't go to just it's not complete. It doesn't just go to a state like it would if, for example, S was an assignment statement. S is something more complicated. So then you take, and you compose S1 prime with S2 using this semicolon in here. And you keep going on your computation with using S prime. Now, if S1 evaluates to a final state, well, then this rule looks kind of like the other one. Well, not really, because you have a continuation. The other rule said you'd evaluate S2 up above in this state, but then you just stop. You say, okay, we evaluated S1 in state S, and in one step we got to a final state. And so then we bring that state down here and evaluate whatever S2 was in that new state. And I think, the way to read this is that this comp standing for composition, comp 1 and rules and the comp 2 rules together say, look, when you're evaluating S1 semicolon S2, finish evaluating S1 before moving on to evaluate S2. Now, I mean, that's kind of the nature of composition, but, it's possible that in parallel computing, you want to have a par operator that says, oh, that should be a semicolon there, that says, and the par operator says, no, really evaluate these two things in parallel. So that should be a semicolon there. No questions? Okay. if rules are a bit different, but not much. It basically just says, look, if B, then S1, else S2. If B evaluates to true, then just evaluate S1 in state S. And if B evaluates to false, evaluate S2 into S. So here you're kind of like counting the cost. If you think of this double arrow, the small step semantics as kind of like counting the number of steps of computation. This is basically saying, oh yeah, the cost of a computation of evaluating a Boolean is 1. It costs 1 unit of time or whatever. Oh, is this the end of my, and then the small step semantics for while are, and this is interesting. I mean, this is kind of another nice way of writing down what the meaning of while is. So if I want to evaluate while B do S in state S, then what I can do is I can evaluate this expression. If B is true, then evaluate S composed with the while all over again. Otherwise, just skip